Hey everyone, this video will be on projectile motion, which is the first section of Module 5, Advanced Mechanics. This is the lesson outline. You can skip to the corresponding section as you wish. Projectile motion is part of the Advanced Mechanics module because it is a two-dimensional motion. This is quite different to the types of motion you've studied in Year 11 because the ones in Year 11, all of those concerned one-dimensional motions. Projectile motion is analyzed in terms of the x and the y directions. Typically, the x direction is defined as either left or right, and the y direction is defined as up or down. The diagrams on the right-hand side demonstrate two of the many examples of projectile motion. You can see in the golf or the basketball scenario, the ball travels upwards and downwards while simultaneously moving from the left to the right. In both cases, the object, that is the golf ball or the basketball, will undergo a two-dimensional motion, hence why it is classified as projectile motion. One of the main reasons why we analyze projectile motion in its two dimensions, the x and y plane, is because there are different forces that are present in each plane. In the x direction, there is no force if there's no air resistance present. In the y direction, there is weight force or the gravitational force, which acts downwards on the object that's in the motion. In all calculation questions in HSC physics, we are making two important assumptions. Number one is that all scenarios have zero or negligible air resistance. In other words, there's no drag force. The second assumption is that the gravitational force that acts in the y direction is constant. In a future video on gravitational fields, we'll learn about why gravity is not a constant value. Any mass in projectile motion will undergo a path that is parabolic in shape. The velocity of the mass at any instance can be resolved into two components: the horizontal component or velocity and the vertical velocity. In the absence of air resistance or drag force, the horizontal velocity of the mass remains unchanged. This is demonstrated by the red horizontal arrow throughout the motion, and as you can see, the length of the vector remains unchanged from the very beginning throughout the entire parabolic motion. In contrast, the blue vertical velocity initially decreases as the ball ascends and increases as the mass descends. This change is due to gravity. So the horizontal velocity remains unchanged while the vertical velocity changes due to gravity. Using initial velocity as an example, let's discuss how we can resolve the velocity into horizontal and vertical components. This is always done by constructing a triangle whereby the right angle triangle's hypotenuse is the velocity itself. The two other sides become the horizontal and the vertical velocities respectively. Typically, when mass undergoes projectile motion, it is launched at the angle theta. Vertical and horizontal velocities can therefore derive using this angle and the initial velocity, which is usually designated as the letter u. Using trigonometry, we can derive the horizontal velocity as u cosine theta and the initial vertical velocity as u sine theta. In addition to trigonometry, Pythagoras' theorem can also be used to calculate the initial velocity if you're given the values of the initial horizontal and vertical velocities. Let's take a look at an example. A projectile is launched at 60 meters per second, which is my initial velocity, u, and an elevation of 30 degrees. So this is my launch angle, theta, that we discussed. Find its initial horizontal and vertical velocities. The first step is to construct a right angle triangle to represent the information given. 60 meters per second, as we said, this is the initial velocity, which becomes hypotenuse, and the angle relative to the horizontal becomes the launch angle, 30 degrees. Here, we can find the initial horizontal and the vertical velocity by using the expressions that we discussed before. So the initial horizontal velocity is the initial velocity times by cosine of the launch angle, which gives us 30 root 3 meters per second. In contrast, the initial vertical velocity is the initial velocity times by sine of the angle, 30 degrees, and that gives us 30 meters per second. After determining the initial velocities, Motion in the vertical axis or direction can be further modeled using uniform acceleration rectilinear equations. These three equations are the ones you should have had many opportunities to practice with in year 11, and it is very important for you to become even more familiar and confident with these equations. In the vertical axis, we are making the assumption that the acceleration due to gravity is constant. In other words, g equals to minus 9.8 meters per second squared. Therefore, when you're analyzing motion in the vertical axis, your acceleration will always be negative 9.8 meters per second squared. In contrast, when you're analyzing motion in the horizontal axis, it is a lot simpler because we are assuming there's no forces acting on the mass in the horizontal axis. So the horizontal acceleration is 0. I'll explain how to use the equations to analyze the vertical velocities and the horizontal velocities through an example. So in this example, the initial vertical velocity of an object during projectile motion is 15 meters per second. The launch angle is 30 degrees relative to the horizontal. First part of the question is to calculate the initial horizontal velocity. When it comes to analyzing velocity, usually what you can do is to construct a right angle triangle where you can link the initial velocity and the horizontal velocity using the launch angle theta. So here, opposite side divided by the adjacent side will give you tangent theta. By rearranging this expression, you can calculate the initial horizontal velocity, which is 15, which is the initial velocity, divided by tangent of the launch angle 30 degrees. That gives us 15 root 3 meters per second. Calculate the vertical velocity 2 seconds after the object's launch. Now, for this question, it is important for you to realize that the vertical velocity of an object in projectile motion does not stay the same. It changes due to gravity, and as a result, we'll have to use one of the three kinematic equations. For this question, this equation will help us find the answer. This equation is useful if we know the time and the initial vertical velocity. From using those two and knowing that the acceleration in the vertical plane is simply 9.8 in the negative direction, so negative 9.8, we can find the vertical velocity after time t. So here, 2 seconds is my time and 15 is my initial vertical velocity. This will quickly give us an answer of negative 4.6 meters per second. In addition to the magnitude, this answer also tells us the direction in which the object is traveling at 2 seconds. The negative sign in front of 4.6 tells us that the object is traveling downwards in its projectile motion. Part C, calculate the instantaneous velocity 2 seconds after the object's launch. While the previous part was asking for the vertical velocity after 2 seconds, this part here is asking for the instantaneous velocity, which is just denoted by v. The magnitude of instantaneous velocity can be determined using Pythagoras' theorem, where the instantaneous velocity is equal to square root of the horizontal component squared added on to the vertical velocity squared. The vertical velocity was calculated in part B, and the horizontal velocity is simply equals to my initial horizontal velocity, because in projectile motion, in the absence of air resistance, the horizontal velocity does not experience any changes due to the lack of forces and acceleration. From putting this in the calculator, we'll get 26.4 meters per second. Since this question does not specify magnitude, we need to also calculate the direction of the velocity, as it is a vector quantity. The direction of velocities in projectile motion is typically indicated by the angle relative to the horizontal. This can be determined by constructing another right angle triangle at 2 seconds, where the vertical side is corresponding to the vertical velocity at that point, so minus 4.6, and notice how this vector is pointing downwards due to the negative sign. The instantaneous velocity is a hypotenuse, and this is the number that we just calculated. The angle theta here below the horizontal line can be calculated by using trigonometry, and using sine theta here, we will get the angle as 10 degrees. The final answer is therefore 26.4 meters per second, 10 degrees relative to the horizontal axis. In projectile motion, maximum height is the highest vertical displacement that's achieved by the mass. Maximum height is affected by two factors. The object's initial launch height, that is where it was launched from, is it on the ground or is it higher up in a cliff? It is also affected by its initial vertical velocity. Faster the initial vertical velocity, higher the maximum height. Vice versa, smaller the initial vertical velocity, shorter the maximum height. Maximum height is not affected by the initial horizontal component, only the vertical velocity. To help you calculate the maximum height, it is important for you to remember that the vertical velocity, that is Vy, always equals to 0 when the object reaches its maximum height. In other words, the instantaneous velocity at the maximum height equals to the horizontal velocity, because the horizontal velocity is the only vector that's present at that point. When you're calculating the maximum height, the go-to equation is this one here, where Vy is 0 as the object has achieved maximum height, Uy is the initial vertical velocity of the object, Ay here is negative 9.8, which is the gravitational acceleration, and Sy is the maximum height. Let me show you an example. The initial vertical velocity of an object during projectile motion is 15 meters per second. What is the maximum height of this object's motion? At maximum height, vertical velocity is 0, and by using the equation we just discussed, we can substitute Vy as 0, Uy as 15, which is given by the question, Ay as negative 9.8, and S here is my vertical displacement, which is the maximum height. That gives us 11.5 meters above where the object was launched. Time of flight is a duration of the projectile motion. Projectile motion finishes when the object returns to the ground or its target. It is important for you to be aware that not all projectile motions will return to the ground. Sometimes the target or the destination can be above the ground or below the ground. Similar to maximum height, time of flight is also dependent and influenced by the initial vertical velocity, not the horizontal velocity. When calculating the time of flight, the go-to equation is this one. Sy is the vertical displacement at which the object finishes its motion, in other words, at the time of flight. Uy is the initial vertical velocity, and t squared here both represent the time of flight. Again, Ay represents the gravitational acceleration, which is negative 9.8. Let's use the same example as before to explain how to calculate the time of flight. So the vertical velocity initially of the object is 15 meters per second. What is the time of flight? In other words, how long does it take until the object returns to the ground? Now, for this type of motion, when the object starts from the ground and finishes its projectile motion on the ground, the vertical displacement at the conclusion of the motion is 0 because it hasn't traveled anywhere in terms of vertical displacement. We can use that information by substituting S as 0, which is my vertical displacement at which the object finishes the motion. Uy is 15 as given by the question. Ay is negative 9.8, and now we can divide both sides by t to simplify the equation. This is then followed by rearranging the equation to make t the subject, which will give us 3.06 seconds as the answer. So the object in this scenario would take roughly 3.06 seconds to travel from the very beginning and finish its motion at the very end when it returns to the ground. The range of projectile motion is the horizontal displacement the object travels at the completion of the motion. The range is perhaps the easiest quantity to calculate because it is considered as a horizontal component, where in the horizontal plane, without any air resistance, there is no acceleration. To calculate range, we can use the same equation as we did for the time of flight. But this time, we have to use the displacement, the velocity, and acceleration in the x direction. So Sx, Ux, and Ax. Sx here is what we are trying to calculate, that is a range. The horizontal displacement the object travels at the completion of the motion. Ux is the initial horizontal velocity, and Ax is actually 0 because we do not have any acceleration in the x direction. By substituting Ax as 0, the entire second term disappears, which gives us a very simple formula whereby the range Sx of the motion is equal to the product of the initial horizontal velocity and the time of flight of the motion. For a given initial velocity, the maximum range, in other words, the maximum horizontal displacement, is always achieved using a launch angle of 45 degrees. This relationship can be better visualized on a graph as such, where the launch angle varies from 0 all the way to 90, and the range always peaks right in the middle at 45 degrees. If the angle decreases from 45, the range becomes shorter. And the same thing occurs if the angle increases from 45 degrees. So when you want to launch an object as far as you can, that is to achieve the maximum range that you can, the best angle to use is always 45 degrees. Let's go through how to calculate the range using another example. In this example, the projectile is launched at 100 meters per second, so that is my u, at an elevation or angle of 45 degrees. It's my theta. What is the range of the projectile? So before you start the calculation, it is important for you to remind yourself how to calculate the range. As we discussed, the range is the product of the initial horizontal velocity and the time of flight. So we need to calculate these two quantities before we can determine the range. To calculate the initial horizontal velocity, we can use the initial velocity and multiplying it by cosine of the launch angle. That gives us 70.7 meters per second. The second step is actually to calculate the initial vertical velocity. I'll explain why we need to do this very soon. To calculate the initial vertical velocity, we'll again use the initial velocity u, which is 100, and multiply it by sine theta of the launch angle. And that gives us the same number, 70.7 meters per second. Now the reason why we needed to calculate the initial vertical velocity is because that is required to determine the time of flight. And we need to determine the time of flight because we need to use it to calculate the range. To calculate time of flight, we'll use this kinematic equation. Remember, at the time of flight, S represents the vertical displacement. So in this question, we are assuming that the projectile returns to the ground, so the vertical displacement at the completion of the motion is 0. Uy is the initial vertical velocity, and ay is the gravitational acceleration, so negative 9.8. And t here is my time of flight. By solving the equation, I get 14.4 seconds. The last step is to use the numbers we've calculated to find and determine the range. The range is a product of the initial horizontal velocity and also the time of flight. And this gives us 1020 meters. Finally, let's talk about energy changes that occur in projectile motion. There are two types of energy in projectile motion. Kinetic energy of the mass that's undergoing the motion and its gravitational potential energy. In addition to these two types of energy, you also need to apply the law of conservation of energy when it comes to analyzing energy changes. Since there are no air resistance, the total energy of the mass at the very beginning remains the same throughout the entire projectile motion. However, when you analyze each type of energy, that is kinetic or gravitational potential, those will change throughout the motion. The two types of energy change in such a way so that any changes in kinetic energy always equals to changes in gravitational potential energy. When the mass is ascending, that is going upwards, its kinetic energy is decreasing while its potential energy is increasing. The amount of kinetic energy that has been reduced by should equal to the amount of potential energy that is being gained by the mass. On the contrary, when the mass is descending, that is going downwards, it is gaining speed, so it's gaining kinetic energy while losing altitude and losing potential energy. The implications of these energy changes is that at the maximum height, the mass has the smallest kinetic energy because it has the slowest velocity. Remember that at the maximum height, the vertical velocity of the mass is 0. At the same time, it has the largest potential energy, and that is because it has the greatest height. Evidently, energy changes during projectile motion occur with changes in vertical displacement. So a mass should have the same amount of energy for each form when they are at the same vertical displacement. As an example, if you compare the object at this point in time versus that point in time, because they have the same vertical displacement from the ground, they should have equal amounts of kinetic energy, that is speed, and also potential energy, that is height.